Who remembers this thing? This is the ZX Spectrum Reactive Device Interface, which allows you to hook up an Arduino and control LEDs and other bits and bobs based on what's happening in the game you're playing on the ZX Spectrum. Cool. I wanted to bring the Arduino into the board and get everything on a one board solution, so we're going to redesign this to use the microcontroller from a Arduino Micro and basically make an Arduino that plugs into the back of the Speccy and gives you access to any information you want in the game that you're playing. Hopefully we can pull it off. So let's have a quick recap. In the first video on this device, we sketched out the idea of the latching mechanism and how it would interface with an external Arduino and what we plan to do with it. In this case, we were using a strip LED to represent the air gauge in the game Manic Miner. After building the prototype on Veroboard using extremely thick wires, we hooked up the Arduino Mega, and you can see here how inefficient the initial design is. We're using 24 pins of the Arduino Mega to send and receive the address and the data buses. We ran some code, talked through it in detail, and we tested it, and it worked. And here you can see it working. I'm playing Manic Miner, and we have an LED strip representing the air gauge. Lovely. So now I'm going to take you through the idea behind version 2 of the design. So bear with me, let's go for the whiteboard. But first, we're going to be using PCBWay to manufacture the PCBs when we get this thing prototyped. Go and check them out. I can't tell you how easy it is to use this service. I'm really pleased with the delivery times and the quality of what I've been receiving. Go check out PCBWay, and thanks for sponsoring the video.
Okay, let's see if I can get the concept across here. So as before, I'm going to draw our ZX Spectrum down here with the Z80 inside. And the Z80 has an address bus and a data bus connected to it. These are available on the edge connector at the back. And we're still going to have to detect when a memory write operation is happening, because that's when we're going to intercept the data on the data bus. So by taking the MREC signal and the write signal and connecting it to something like some NOR gates, we can create a, let's call it a latch signal. And this is going to go into our microcontroller. And as I mentioned in the intro, this is the same microcontroller which we find on an Arduino Micro. I think it's a Micro. And it is an AT Mega, sorry about this pen, 32U4. Now this has 44 pins on it, and I think something like 26 of those are I/O pins which we can use, and they're arranged into ports. So we're going to use an interrupt enabled input pin for our latch, so we can fire off an interrupt on the code that we're running on the AT Mega and execute the routine to read in the data. And how is this going to work? Well, the previous solution, I think we used 24 pins on the Arduino Mega, which we were using, which obviously isn't going to work. So we're going to use port B, and port B has 8 input-output pins, which we can use. So we're going to treat that like a bus, an 8-bit bus. And the way we're going to do it is we're going to take the address bus out of the Spectrum, and we're going to run that into 2 chips, and these are going to be 74LS257 chips. So there's 16 bits on the address bus, and 8 will go into one chip and 8 will go into the other chip. The data bus is also going to be taken out, and we're going to put that into a 74LS244 chip. Okay, what happens next? Well, we're going to have a output from our AT Mega, which is going to go down to these 257 chips. We're going to call that a select. And what this is going to do is it's going to switch the output of these chips to either the first half or the second half of the address bus, because you only get 8 bits out of these chips, right? Those are going to come out in a bus over this way. Now, we also have to have another output from here, from our AT Mega chip, which we can call A/D. And this is going to select between data and address, and I'll explain in a second. The 74LS244 chip outputs 8 bits as well. And we're going to join the outputs of this to the outputs of the 257 chips to create a data in bus. Let's just call it data in. Now by controlling A/select and AD, and given that these chips have tri-state outputs, we can choose to either have the first half of the address bus the first half of the whole data bus, or the second half of the address bus, coming in on our input pins on port B. Should have drawn it over there. So what's going to happen? We're going to detect a memory write operation. We're going to generate the latch signal. This is an interrupt pin. This will immediately, or as quickly as possible, cause the ATmega to cycle through reading in the half of the address bus, the second half of the address bus, and then the data bus. And we can read them in with some nice input commands, which will very quickly latch in this data byte on port B. And the hope is that we'll be able to do this quickly enough without any extra chips to do any latching with hardware outside of the chip. And we'll be able to read in the address and the data values quickly enough on the 16 megahertz ATmega chip to then do what we want with it within here. This is going to be functioning like an Arduino, and we're going to have however many pins which are available to us to do whatever we want with it. Control our LEDs or displays or motors or speakers or whatever. So that's the premise. If we can't latch this in fast enough before these values all change again, then we've got a problem. We're going to have to bring back the latching circuit which we used on the first iteration, which is going to require having 3 or 4 more chips. So let's see how we get on.
I do want to breadboard this up rather than going straight into a PCB design, so I've bought these breakout boards for the ATmega chip. They're double-sided. There's a TQFP44 package on the top, and on the bottom we've got a smaller one which is not the one we're going to be using. So my first job is to attach an ATmega chip to this board, put some headers in it and stick it into a breadboard. Quite like this. I've got a few spares now, so lots of fun ahead experimenting with microcontrollers. Speaking of which, this is the package that the microcontrollers came in. They're all just sandwiched in between this foam. There it is, ATmega 32U4. This is the same chip which is on an Arduino Micro. So let's see if it fits, see if I've bought the right part. Should be fine. Line up the little marker for pin 1, and yeah, perfect. We shouldn't have any trouble soldering this in. Here's one last close look at the chip before we go ahead and nail it down. I'm going to do this with solder paste and hot air because I quite like that. That's a method I've been using with some previous builds, and as you'll have seen that I've been working on my soldering technique, so getting better at this. Hopefully not put too much solder on there, and we can pop the chip in place. And it's time to go to the microscope, apply some hot air and get this thing soldered down. Okay, here we go, and I can see that I probably have used a bit too much. There's a bit of bridging going on, but the next step is to apply some flux and drag the soldering iron tip around to neaten up all these connections and tidy up these solder bridges. So just repeating the process of applying heat, a little bit of flux, dragging the soldering iron tip around and tidying up the bridges. With that done, I'm going to do a quick sanity check for continuity by checking continuity between adjacent pins to make sure I haven't shorted anything out and everything seems fine. Now we just need to solder in our headers. I've got a few 1x20, so I'm doing them first, and I'm going to put a 1x2 in the ends to finish the job. Okay, looking good, nice and straight. That should pop into our breadboard nicely. This is the breadboard I'm going to be using for this part of the circuit, and with any luck the holes line up, and they do, almost as if it was designed that way. So what are we going to do? This is a schematic of an Arduino Micro, and we're going to basically recreate this on our board. So let's go around. This is a 5V selector for choosing between external power and USB power. I'm not going to put that on the breadboard, don't need it yet. We don't need a 5V regulator because we're only going to be providing 5V to it. And this is our USB input, which we will have. We will have a USB port providing some power and our data. This is for flashing the ATmega chip, more on that later. We're not going to put that on our breadboard because we can just do it with wires. We will need to put that on the PCB though. These are just LEDs attached to the ATmega chip, we don't need them. And this large chip here on the middle left is the ATmega chip, and we already have one of them, which is nice. Over here we have the crystal oscillator, 16 MHz, we definitely need that. We'll get one of them for our breadboard and we'll put an SMD one on the PCB. We have a reset circuit which we're going to put in because that seems useful. And that's about it really, that's all we need to worry about, so let's start putting all of those components on this breadboard. Starting with the USB connector, here it is, very simple, it just has VCC, ground, D minus D plus and ID, whatever ID means. We'll solder a header onto there and slot it into our breadboard. Nice and easy. I will be using USB-C on the PCB, but this was just a cheap and cheerful simple way to get this thing up and running. This is our 16 MHz crystal. We'll stick that in the appropriate place as per the schematic. The crystal needs 2 load capacitors on it, which go to ground. So we'll put them in, we're going to link them together with a little bit of wire and send that off to ground. If you're worried that I'm using red to connect to ground, well, wait and see how messy this is going to get. That's pretty small fry. Now I'm just hooking up the data in pins from the USB connector as per the schematic, with a little bit of simplification. And the rest of this now is just kind of attaching all the various VCCs and grounds, our reset switch as well, and we should have our Arduino pretty much recreated on the breadboard there. Lovely. I'm plugging it in here because I haven't yet learned that I need to flash a bootloader to the 80 mega chip. We'll get round to that. Now I need to get the address bus and the data bus and a few control signals out of the ZX Spectrum, so I'm going to make a reusable breakout board for myself. You can buy these, they are available if you go googling around, but I thought I'll just make my own since I'm getting to grips with this Veroboard stuff. So here we have an edge connector, a whole bunch of sockets, and I'm going to start attaching wires. I'm using thinner wires now than I used to use. I'm going to label it all up as well so I can reuse this in the future. There's our data bus, address bus is on the back, and we just need to add some of the control signals. So I've taken a selection, stuck them here, and I've put a reset switch on it. Lovely. Let's continue the job and start building the logic side of our circuit. So these are our 3 chips which are going to offer up the address bus and data bus to our Arduino. Let's get the jumper wires out and start making a big mess. I'm going to hook up the breakout from the ZX Spectrum to the left sides, like the input side kind of this breadboard, and I'm going to try and join that up to the Arduino which we've made on the right hand side. I'm using a little red breadboard as a kind of bridge just so I can keep track of what's connected to what, and these wires are getting quite long. I'm crossing my fingers that it's going to work. It always amazes me how compact you can make these circuits after you've seen them breadboarded up and you put them onto a PCB design, so I'm very excited to get the first prototypes through and start building this up with SMD components. Here we go, just attaching up the 80 mega chip, and we should be ready to start experimenting with this thing. And first of all, I'm going to plug in the Spectrum with everything hooked up and just check that it doesn't crash and it boots up correctly, and it did, so everything seems to be okay so far. But as I mentioned, you can't communicate with these chips until you flashed a bootloader to it. Now you can get USB devices that do this for you, or you can find guides online on how to do it with an Arduino, which is what I did. I'm not going to repeat that guide here, but it involved using the Arduino interface here, the IDE, to go to Programmer and Arduino as ISP. With that, I was able to flash an Arduino bootloader to the 80 mega chip. I'll put a link in the description to the guide, but I was muddling through this, so I'm not the person who should be explaining this process. I did, however, buy one of these from Amazon, so in the future I can flash this much more easily. See the block connector on the left? We're going to have pins on our PCB, which these can plug directly into. So at that point, I was able to plug it in and use a logic analyzer to see what was happening. Now, as a reminder, we're looking for a latch signal to be generated. That's in the right there. The 80 mega then executes an interrupt routine. We'll have a look at the code for that in a second. That produces an A select signal which chooses between the first and the second half of the address bus, and it produces an A/D signal which chooses between the address and the data bus. And what we're looking for is for all that to happen before the memory is written to. Again, it has to happen quite quickly, otherwise we're going to get data which doesn't correspond to the address which we're interested in. So let's have a look at the trace. In orange at the top we have the latch signal, so you can see that we've got 2 rapid memory write operations happening one after the other. Each of these in turn would have generated a latch signal, the first of which would have set off our interrupt routine. So after that first latch signal, the interrupt routine starts, and the next thing that happens is it starts reading in the address bus, and the yellow signal corresponds to the A select. So while it's low, we're reading in one half of the address bus, and while it's high, we're reading in the other half. Once that's been read in, we switch A/D at the bottom there in blue so we can read in the data bus, and you can see that this is happening during the next memory write operation which the ZX Spectrum fired off. So basically it's too slow, and I tried my best to optimize the code, but it's just too slow. So now we're into plan B. Now what plan B is going to do is we're going to use another output pin of the ATmega, and we're going to call this hold. And the way this is going to work is whenever there's a latch signal generated, the first thing that the ATmega is going to do is generate a hold signal which goes back into the NOR logic down here. Now our latch signal coming in here is going to be totally dependent on hold, so we won't generate a latch while hold is high. While hold is high, we're going to have some extra logic on the address and the data bus. This is 74LS374 chips. This allows us to latch the values. There'll be 3 of them, 2 for the address bus, 1 for the data bus. And whenever we generate a latch, it's going to come over here and cause it to refreeze the address and the data bus. And that holds everything in state so that we can read in the address and the data bus into our ATmega, giving us a little bit extra time that we need. And then the ATmega will reset the hold signal and wait for the next latch to happen. Unfortunately, this means 3 more chips have to be on our design, but that's the way it is. We could use a different chip altogether which is faster, but then it wouldn't be an Arduino, and I really want it to be an Arduino, so let's see if we can get it to work. Okay, I've hooked up the latching logic from the version 1 of this device, and we can take a look at what's happening. So again, we've got memory write operations at the top there in orange, and then we see in purple this is the wait or hold signal which is generated when the interrupt routine starts. So the first latch there triggered the interrupt. The second one will have updated the address and data bus, but that's okay because the routine hasn't started yet. By the time the routine starts and the wait signal or hold signal goes high, which is this purple one, everything is latched and stuck in state. Now A select goes high, we read in one half of the address bus, it goes low, we read in the other half of the address bus, and then A/D goes high, that's the blue one at the bottom, and we read in the data bus. Finally, we undo our wait signal or our hold signal, which is the purple one, and the system is ready to listen for another memory write operation. Okay, quick look at the code. Now this still needs to be optimized, but basically we're defining a few variables, a 2-byte variable for our address, a 1-byte variable for data. Now in our setup, this is the important bit, the setup bit, I've put some comments in about which of our pins corresponds to which of our inputs and outputs, and we're going to set up these ports. We're going to do it with some pretty low level coding, and I'm not doing a tutorial here because I'm muddling through it myself. And don't worry, if you want to use this thing, you don't need to code like this, because this will just be a bit like a library you can call on. So our setup routine. First of all, we configure port B as inputs. That's where we read in our address and data bus 1 byte at a time. Now for port C, we're going to configure the A select signal on port C pin 6 and the D/A signal on port C pin 7 are outputs. Next, we have port E, and I'm using port E pin 2 as our hold the latch output. And port E pin 6 is the input that our latch signal comes in from the logic, the NOR gate logic. We turn off the pull-up resistors on port B. That's important because it is an input and we need to see what's happening. We can't just force the inputs to be high. Now for port C, we're going to start by setting A select high and the D/A signal low. So when the interrupt routine sets off, we can immediately read in 1/2 of the address bus. The 2 commands at the bottom, the EIMSK and EICRB, are for setting up the interrupt pin. So we have an interrupt pin on port E, pin 6, and we're going to be using it when the latch signal fires off, so we have to set that up appropriately using bit masks. I have a simple loop running with a 100 millisecond delay, and what this does is it just prints out the data at address, whatever address it is that we're looking for is, and then whatever data we detected at that address. And that only happens if the Boolean flag found data is true. Now here's our interrupt routine. Again, this is kind of low-level coding, so bear with me because I'm probably not explaining this very well. The interrupt routine, which starts ISR brackets int 6vect, is going to execute whenever we have an interrupt detected. That's our latch signal. So you'll see we basically set the hold signal to on almost straight away. That prevents the data and address buses we want to read from updating anymore. We hold a select high, and I don't need that line of code actually. I told you this could be optimized. Anyway, we have a couple of NOPs in there, and a NOP just waits a little bit while the slower ZX Spectrum sets up all of its bits. And then we read in the address, which is P in B, the command on line 47. We read in port B, and that gives us the first half of our address bus. We now swap the output of our A select to low. That's the port C command on line 49. We have a couple of NOPs again just to let everything settle down, and we read in the second half of the address bus with a clever command which kind of combines it with the first half to give us a value. Now we change the output of our D/A signal, so we're looking at the data bus. We read that in after a couple of NOPs into data temp. And now we do one more operation here, which is on line 58, that says if the address is the one we're interested in and it's new data, then we have found the data we're interested in, we found the address bus we're interested in, we set the flag to 1, and the code starts outputting. So it outputs to our serial monitor. Here it is. Now here's one iteration of the code which was working. I'm running a program on the ZX Spectrum which just counts up. It writes to address 55555 a value from 1 to 255, and it just increments it. And I'm telling the Arduino which we've created to look for what's at address 55555, and you can see that it's working. It's reading out the incrementing value correctly. Okay, cool, it works. Pleased with that. That it's taken 20 minutes, but in reality it took me a couple of weeks, spending evenings here and there tinkering. So I'm really happy about that, and we could be using this now to drive our LED strip like we saw in the last video. But I want to make this neat, I want to put it onto a PCB, so I drew out the schematic using KiCad, here it is, with all of our many chips on there. We can have a quick look around. So here we've got a little bit of logic, NOR gate logic, and the other 3 gates of the chip are down here in the bottom right, generating our latch signals and such. This is our 2x3 connector for flashing the 80 mega chip, which is going to be very useful. The 80 meg is up here in the right, and I have included the MOSFET, which is for switching the power supply from USB to external, which will be our ZX Spectrum power supply. Heading over to the PCB layout, this was a pig to root, and I've used a 4-layer PCB with some planes in the second and third layers. I don't think I'm very good at doing planes yet, but it works. It passed the checks, and I was able to get it manufactured. Here's a look at it in 3D. Looking cool, but looking busy. And actually, while making this video, I realized that I can get rid of 3 chips from this design. The latching chips that I brought in when we went to plan B have tri-state outputs. So I can just use logic from the 80 mega chip to switch these outputs on and off these 3 chips and cycle between our address bus halves and the data bus. And if I can remove 3 chips from the design at the cost of maybe 1 more output pin on the 80 mega, this board's going to look a lot more neat. I could do it with a bit more logic and save the output pin from the 80 mega that I would need to choose between these 3 chips. I'll have to think about that. Anyway, I did go ahead and finish this design before I had that realization, and I did order it. So let's have a look. The boards have arrived already. There it is. This is our prototype, and I'm looking at it now while narrating this video, thinking how much neater it's going to be with those 3 chips removed. So I'm going to flesh out that idea, but for now we're going to get on and build this in the next video. I've got a fancy new microscope to play with, and I'm looking forwards to trying this out. So we'll build that, get it working, and then work on another iteration. Well, I hope that made sense. I hope it was interesting. Thanks for sticking with me to the end, and I'll see you in the next one.